In this video, we're going to see if we can revive this ancient piece of 80s tech that was made obsolete by the digital TV transition. This is the Sony Watchman. It has no means of getting video onto its tiny little screen other than via its antenna. And there are no analog broadcasts, at least not in the United States anymore. So it made me sad to think that the Sony Watchman is forever doomed to just be turned on every once in a while and play static. And I wanted to see if I could do more with it. Could I use the experiments I've been running with my Raspberry Pi Pico high-speed DAC, where I successfully generated an AM radio signal, to generate a little mini pirate television station that would play on this Sony Watchman? Let's find out. It is a fascinating little bit of tech from the 80s when the Japanese were just on a roll. They were miniaturizing everything. They had a huge hit when they took the cassette player and put it in your pocket and you could carry music around with you all the time. That was just an amazing innovation back then. Like, it was just mind-boggling to be able to do that. Nobody thought it could be done with a television. And it turns out nobody much cared. But they did produce a lot of these. I think it mostly went to sports aficionados who just couldn't stand to be away from the game. So they'd stick this in their back pocket or their briefcase and take a little peek and see, how the Dodgers were doing or how the Cubs were losing.
Go Cubs!
But it is basically a piece of e-waste nowadays because all it supports is analog over-the-air television. There are no audio or video input jacks, although they can be modified to accept a video input. I haven't done that, and I'm not sure I'd want to because it would kind of, ruin the beauty of this thing. In case you're wondering what the heck this thing is just floating around, I wondered that for several days after I first owned this until I figured out it's a little kickstand, right? See, maybe back here. There you go. It sits up just like that, and you can watch it. We first need to talk a little bit about the structure of a television signal. And this starts with composite video. Composite video is the oldest television standard in the planet. It defines a standard that's intimately linked to the mechanisms of old tube televisions. There is almost a one-to-one direct analog mapping between a composite video signal and the motion of the electron beam in a tube television as it scans across the phosphors on the front of the screen. So let's start talking through this composite video standard. It starts with the scan line, and a scan line is 62.5 microseconds. This corresponds to one horizontal display row, and this scan line is broken out into different portions. So there's the H-sync portion, the back porch, which comes first, which is a little confusing, the active portion, which actually contains the pixels, the video information that's going to be displayed on your screen, and then the front porch, which comes in the back. I don't know. Somebody tell me why that is in the comments. I don't know. And there are timings that are associated with them. So they all have to total up to this 63.5 microseconds. And these are relatively precise. You can fiddle around with them, but if you go too far outside of spec, you're going to generate a signal that a television isn't going to lock onto. So during this scan line, the spec necessitates that the composite video signal hit a number of different voltage levels. The sync level is the lowest level. It's an unambiguous signal that the television needs to do something important. And so you can see the blanking level here at the beginning of the active, before the active area, and at the end of the active area. That's meant to blank out the electron beam for when the H-sync sends the beam back to the beginning of the line. So you don't want to see that beam tracing across the screen when it's doing that. And then you have the active area, and this is where the horizontal scan line actually sends the picture data. So you get various voltage levels between white and black, and that sends the luminance of that particular pixel. Interestingly, there is nothing in the spec that says what the horizontal resolution is. You can send as much information as you'd like in here. Your television set might just not be able to do it. So this is a progressive scan hack. Normally, in normal television, they are interlaced. So you send two different frames and they are interlaced or interleaved together. So you send the first half as 262.5 scan lines. And I'm not exactly sure how you send a half of a scan line, but whatever. And then you send the second half and they interleave within one another like that. So you send one frame like this and one frame like that and they interleave. And we ignore everything in the spec around interleaving. It's relatively complicated to do and we don't need to. And it's actually really cool because it gives you a 60 frames per second output. And 240p is probably more than enough for what we want to do. And actually, it was more than enough for game consoles. This is exactly what game consoles did. Most game consoles had a resolution of 320 by 240. And they use this exact hack. It's not really in spec, and no broadcast television station was ever allowed to transmit a signal like this, but it was very, very common for game consoles to do this, and that's what we're going to do. And let's look at the math here. We have 263 scan lines times 63.5 microseconds per scan line. That gives us 16,700 microseconds per frame, or approximately 1/60th of a second. So that means we're going to get 60 frames a second. So let's put this all together and see what we get here. This is kind of a conceptual picture of the entire signal that we're sending. So kind of horizontally, we have the scan lines, and then as we go down, we get into something called vertical sync. Once we're done sending our picture data, once we're done sending those 240 lines, we still have 23 extra lines to send, and those are not like the scan lines that we saw before. They are vertical sync. And that gets relatively complicated, and I hacked around with this quite a lot. I found something that seemed to work okay and lock on okay, but this is very important. The vertical sync is important for signaling to the television the beginning of your frame. And if you don't get vertical sync right, you get a rolling image. And I don't know, if you are of a certain age, you might recall rolling images. And there was a vertical sync knob that you could twiddle to kind of adjust that lock if the signal were weak. So sometimes if the signal is weak, it messes around. It's very, very analog. It messes around with that vertical sync, and the television can't interpret it right, and it rolls. We have 240 scan lines for the active video portion of the screen, and then we have 23 scan lines for the vertical sync, and that makes up that 263 scan lines that we were talking about previously. I wanted to talk a little bit about how the beam path figures into this. Every single portion of the composite video standard has a component in the beam path. The back and the front porches signal to the television that it needs to blank out the electron beam for movement. H-sync signals that the beam needs to return to the beginning of the line, and then vertical sync signals that the beam needs to return all the way up to the very beginning of the picture. How do we send a composite video signal over the airwaves? Well, what we have to do is we have to generate a 55.25 megahertz carrier frequency. We take a high frequency carrier signal and we amplitude modulate a lower frequency envelope. So the outer envelope is this composite video signal that changes relatively slowly, and the inner envelope is our 55.25 megahertz carrier signal. Here we can see the sync, the front porch, the active portion sending a couple pixels worth of data, and then the front porch on the end. So this is one scan line amplitude modulated onto a higher frequency carrier signal. And then we do all of that for all the scan lines, and then for the vertical sync scan lines, and we've got an entire picture modulated as a radio frequency signal that hopefully this guy can pick up and display. Hopefully we can bring it back to life. What do we need to do to actually get our Raspberry Pi Pico DAC to generate this composite radio frequency and actually become a pirate TV station? This is the carrier frequency that we have to hit. It's 52.5 megahertz. So it's the lowest frequency on the TV spectrum. So I have the best chance of hitting it with my low-powered microcontroller. This is channel 2. Does anybody know what happened to channel 1? Would it have been even lower? I don't know. Let me know in the comments. My Pico DAC in my previous testing maxed out at 150 megahertz. 55.25 megahertz is definitely less than 150 megahertz. So do you think it's doable?
It's doable. definitely doable.
I think it's just doable. If we lock the microcontroller at 222 megahertz and do 4 DAC samples per wavelength, that gives us 222 megahertz divided by 4 DAC samples. It's 55.5 megahertz. That's close enough to 55.25 megahertz, right? Right?
Close enough.
So let's break it down even further. If we divide each scan line into 3,528 words, one word is 4 DAC samples or 1 wavelength of the carrier. That gives us 3,528 times 263 scan lines times 60 frames per second gives us 55.6 billion. Well, that's close enough to 55.25 megahertz, right? Right?
Our judges indicate that that's close enough.
Our next step is we've broken down those scan lines into those 3,528 word buckets. We form a bucket brigade to shovel those words in memory out to the I/O ports. So we use DMA, which is direct memory access. This uses little to no CPU to move buffer 1 to the DAC. So we shovel bits from the scanline buffer using DMA to PIO, which is the programmable I/O interface, and then PIO shovels those out to the I/O pins to our DAC, which generates our analog carrier level. And then in the background, as DMA is doing this without CPU intervention, the CPU is free to then build buffer 2 from the frame buffer. And then when everything is done, we swap buffers and repeat. We just keep doing the bucket brigade. And then we do the same thing for the frame buffers. The frame buffers are 320 pixels by 240 pixels wide, and frame 1 is being read scanline by scanline, copied into the scanline buffer and off to the DMA process, what we just saw in the previous process. And then we have frame 2, which is free to be written to by the core game logic, and this is done actually on a second core. You wouldn't want to write to frame 1 while frame 1 is being copied out via DMA to the DAC, because you could get video corruption, you might get tearing and so forth. So we use this double buffering to make sure that we're always writing to the background buffer and not the buffer that's being copied out currently to the I/O ports. And then when we're done, we swap buffers and repeat, and then we get buttery smooth 60 frames per second. I've got my Raspberry Pi Pico wired up with its little poor man's DAC here, which is just an R2R resistor ladder that converts the digital pulses that we're making into an analog output. And so what I started to do to make this was just to make the composite video signal. You can see the horizontal sync interval, you can see the back porch, you can see the data portions, and then if we scroll out a little bit here, you can see basically this is sending all of the data, the various different luminance levels for a particular scan line. And then on the back, you see the front porch, and then back to the horizontal sync again. So this is a relatively simple signal to make. It's relatively low bandwidth. You can see it's got 15.7 kilohertz here. If you're old enough, you might remember the whine of an analog television sitting in your living room. That's the sound you heard. Now, my ears probably can't hear that anymore, and this device certainly is not making any sounds like that. But that 15.7 kilohertz was the characteristic whine of a television, and it came down to the electronics processing the composite video signal underneath the hood. This is great and all, but when we take a look at my Sony Watchman, it doesn't have a composite video input. So I can't do much with this composite signal. Even if these little bits of data were making meaningful scan lines, there's no way for this Sony Watchman to interpret it. We form a radio carrier, so a 55.25 megahertz carrier frequency that we modulate, we AM modulate it with this particular envelope. And I can show you what that looks like right here. Okay, so if we zoom out a little bit, we can see the individual horizontal scan lines. Every little block here is a horizontal scan line, and the cut in between them is the horizontal sync. If we zoom in a little bit here, we can see the horizontal sync, the back porch, so we can see the individual data. So these represent different luminances for the various pixels on the horizontal scan line. And then all the way to the end here, we see the front porch and then the horizontal sink of the next section. And if we zoom in, we can see the 55.5 megahertz carrier frequency we're modulating this AM envelope to. So the outside of this envelope looks like the composite video signal that we saw in the previous example. So the tuner inside of the Sony Watchman should be able to decode a signal like this. I don't think it'll do a very good job with this signal because this signal is missing a lot of details. It doesn't have a vertical sync. Let's see what it does. Yeah, it's seeing something, because definitely if I unplug it, it goes back to static. You can see some vertical bars there, but there just isn't enough proper signal for it to latch onto. Here is the actual video signal that I developed that has all of the components that you need. It has the horizontal sync and it has the vertical sync and the vertical blanking intervals and so forth in order to get an actual television to lock onto it. What you can see here are the vertical bars are the vertical hold or the vertical blanking interval, and in between are the frames, and you can actually see the data going back and forth here. So you can see a ghostly impression of the image. We're going to be able to see something like what we're seeing. There's something bouncing around on the screen. You can actually see that in the horizontal scan lines in between the vertical blanking intervals. So let's go ahead and show that. I'm not sure how well this is going to show in here. So you can see it's the Signal Drift logo just kind of floating around the screen like in a screensaver. All I'm doing for a transmission antenna is this, and you can see that it actually is working because when I unplug it, you get a much worse signal. Okay, so we got a little surprise here. Let's see what we got. Go ahead and load this. Some static, wait for it, wait for it. Here it comes, it's loading. It's loading. This could take a little bit while. I mean, it could take a while. Okay, I don't know if anybody's ever ported Doom to the Raspberry Pi Pico, but getting Doom and this radio frequency analog television, black and white television generator working on the same Raspberry Pi Pico certainly were not into my time budget. But I was able to port a tiny little game to the Raspberry Pi Pico, and I'll show you that next. But I still think this is really cool. That's a nice little capture of the Doom logo in grayscale, and it's playing beautifully on this Sony Watchman over the airwaves. And again, just to prove to you, there's no smoke and mirrors. Like, there's no wire connected to this. It's definitely going through this little antenna here. And I've got my little paddle controller here. And we've got advanced AI taking the computer side. He never loses. He never misses a point. So damn it, I'm already behind. I was distracted. The best that you can hope for is a 0-0 tie with this advanced Pong AI. It truly is groundbreaking. But isn't this cool? I'm playing a real little video game on a tiny microcontroller, broadcasting the signal over the airwaves to a Sony Watchman. We have truly resurrected the Sony Watchman. It is doing something usable and useful. I'm gaming on it. Well, that's a wrap. I think we successfully revived this little piece of potential e-waste. I want to package up my little Pico DAC into a little console so that I can come along and play Pong every once in a while. And if I ever encounter an old black and white TV in the future, maybe I can whip this out and play a little game on it. Thanks again for watching. This has been Signal Drift.